another person doing that to me, I cannot do that. So I don't know how this thing are going on, okay? But anyway, let's try.
Okay, so are you able to see my screen?
Yeah, I'm seeing your screen.
Okay. So I can move your slides. Please continue with your presentation.
Okay. So good afternoon, everybody. Sorry for this little problem. I have the plan to do in person, but it was not possible. I am in a jury in Brazil, so I have to stay here. Sorry for that. So I'm going to tell you something I have done in the last 10 years concerning the conversion of the biomass into regular hydrocarbons. Okay, so our approach is able to produce drop-in fraction in the gasoline or jet fuel, also using the refining structure or made new entirely refinery structures. Okay, also the price is competitive to regular oil. You can move to the next, please. Yeah, just to let you know, some talk about motivation, and then we jump to the technology approach, and in the end, some outlook or this global view to the presentation, the technology we have done. Please, the next one. So energy, the use of energy has shaped ourselves because we have eaten boiled food, so it change our morphology, and also we have enough energy to provide the entire green fuel production. We have used quite a lot as human being, but the earth itself has received much more energy from the sun that it can be transformed. It is transformed in biomass, wind, and several types of renewables. The next one, please. So this just to let you know that you have enough biomass to produce regular fuel. For example, if you download the billion-ton report, United States, for example, is able to produce 1 billion ton of biomass, and even more than that. And 1 billion ton of biomass is equivalent of 4 million barrels a day of oil. Just to let you know that Brazil has already produced 4.6 billion tons of biomass. That it means something around 2 million barrels a day, and you have produced 2.8 million a day. So when you consider, for example, in a general view that the fuels consumes 40% of the energy, and you have 10 times more energy in the biomass. Biomass is a powerful source to produce fuels like LPG and gasoline and jet fuel and diesel. The next one, please. So it's not a new idea to produce hydrocarbon from biomass. Some of the approach, I think that you know that. We can talk about if you want later. Some of the approach has more than 50 years, and there are some good points and drawbacks in each of them. I'm not going into detail. I just let you know that our way of producing fuel from biomass is completely different from those you are listening in these slides. Please, the next one. So another thought. Okay, so basically, we're convert the biomass into hydrocarbon. I just represent the cellulose. It's on the top left part side of the slide. Then the end cellulose and in the end the lignin. One third, please. So the idea is just to convert a low density material that you namely biomass that's a little bit more reactivity than hydrocarbon into the regular fuel. One more. So basically, I'm talking about how to remove in a new way the oxygen that's present in several biopolymers in the biomass. The next. How you do that? We use basically 2 steps. First step is convert the biomass into a new product, you namely biopetroleum. use mild conditions to avoid several parallel and undesirable reactions in the presence of ketones and in diluted acid as a catalytic amount. And then we convert the biopetroleum using cracking or hydrotreatments or a hydrodeoxygenation process. So in the second step of the approach, we convert the biopetroleum into regular fuel, as you see in the right side of the picture. Yeah, the yellow one is when you use the cracking process, you produce a little more gasoline, and the white one is when you use ADO process. I'm going to show you that the combined use of both processes are able to produce fuel like the one you use in your car, home, and etc. Next. So just to let you know that the biomass is quite reactivity. For example, when you decide to do a flan, if you don't take care with the sugar, we transform sugar into a coke. So this is an example of parallel and undesirable reaction that biomass is undergo if you don't take care of. In another thing that you have to take care of is to try to preserve the carbon-carbon chain, because fuels as gasoline, for example, that's something in between 5 and 12 in carbons. So try to avoid the production of, for example, like gasification that will increase a lot the entropy, then we have to come back to building carbon-carbon bonds. Okay, next one. So in our vision, we have to convert biomass into a stable liquid. Now you know that you named this as biopetroleum that try to contain similar class of compounds and a good density to be sequentially processes in several types of reactors. The next one. So how you do that? You use protective reaction. We can use several types of ketone. This is an example of using acetone, producing isopropylene groups. So when you do that, you decrease the amount of free hydroxyl groups. And this is the main reason that you avoid parallel and undesirable reaction of the biomass. When you convert the biomass into biopetroleum, then you can control a sequential conversion into hydrocarbon. Next one. This is the first part of the approach. So I'm going to tell you how you produce the biopetroleum. Next, please. So how you do that? You use very simple reaction condition. It can be a tube, it can be a batch reaction. Use low temperature in the presence of ketones and acid. And you, next one. Next one. So just to let you know some properties of the biopetroleum. You see good density, viscosity at 40 Celsius degrees. Is similar, a little bit is similar, you can pump that at 40 Celsius degrees. The composition is very low in nitrogen. The composition depends how you prepare the biopetroleum. Stability is quite good, up to 3-4 months. So now the next section is I'm going to show you how you convert this type of biopetroleum into the target products. Next one. You see on the just some insights on how to produce the biopetroleum. You see that on the left part of the slides, you see that you can see, for example, the red one, that's a type of sugarcane bagasse. You can obtain full conversion. Also, the blue ones is also sugar bagasse, but it's a little bit different. If you increase the temperature, you are able to convert all types of carbohydrate. Sugarcane bagasse has around something between 70 and 75%. In our case, we obtain more than 75%. So the conversion of the sugarcane in the biomass in general start remove the hemicellulose, then we go to the amorphous cellulose, and then the crystalline one, and in the end you have more lignin. You see some pictures of how we disconstruction the fibers of the biomass. This is all the results are already published. Okay, next one. So now we jump to the second part of the presentation. That's how we convert the biopetroleum. Next. The first slide says it was published 10 years ago. So I like to show you the proof of concept that the carbons from sugar is converted into hydrocarbon. For example, we see that we use the carbon-13 in the sugar part and regular isotope distribution in the isopropylene groups. You see, for example, when we use the label one, we have the black bar, and we use the regular ones, we got the white one. You see that this distribution are remarkably different. Much more, several amounts of carbon-13 is incorporated into the products. A little bit more interesting, it's that some of the products is full of carbon-13. So it means that the sugar is converted into intermediate that is going to produce the final hydrocarbon. Yeah, we know a little bit more than reaction pathway. It's not the idea to go deep in that, but you can do questions if you want. So the main conclusion of this slide is that sugar carbon is remarkably incorporated into hydrocarbon. Please, the next one. Another result that's quite important is the stability, that you increase the stability by protecting hydroxyl groups. For example, when using an open empty reactor, no catalyst, we pump glucose in water at 500 Celsius degrees. You see that almost 50% is converted into coke. When you do that, using a representative compound of BP, no coke, and also a very low degradation molecules. You see that 0.12%. So it means that the protective reactions are effective to avoid sequential and undesirable reaction of biopetroleum. You see, of course, that in the next slides that a remarkable amount of carbon from biopetroleum is incorporated into the product. The next one. Then we move to the fixed bed reaction. I think that all of you are familiar, but if not, we pump a solution of BP or representative compound into a fixed bed reaction. So you put the catalyst in the part one, the number one of the picture. So then we condensate the leaks fraction and the gas we analyze online, yeah, by a GC. Okay. So in the catalyst, in the reactor, you can explore several types of catalysts, as you're going to see in the next slide. Please. It can be this one, just to let you know a broad distribution of product. The first point I'd like to call attention is it's 7.5% of the X is converted into coke. It's very low indeed. And then we have hydrocarbon, that's aromatic, olefins, and cycloalkanes. It's more important that this representative compound of the X has 65% of carbon and hydrogen. 43% is converted into useful products. Useful products is everything excluding coke, CO, and CO2. So when you divide them, we observe something 66% of carbon and hydrogen from the X is converted into the final products. Next one. Here you explore several types of zeolites in a fixed bed reaction. We mix this modern compound on the left side part of the figure. We mix with NXN. Then we use several zeolites. You see, for example, 3 of them. And it's quite important that when you convert the X and the hydrocarbon, more or less the types of zeolite affect similarly both of molecules. For example, the SM5 is well known to produce gas and liquid, and a little bit more olefins and aromatic, and it's the same when you use NXN and DX. Why zeolite? That's well known zeolite used in the FCC process produce more liquid and more coke. And you observe that for NXN and DX. So in a general sense, I'm telling you that the catalyst is able to control the DX, it means the conversion of this representative compound of BP. Of course, I'm going to show you soon that BP follows the same thing of DX. Okay, next one. So now it's an example of ETO process, hydrodeoxygenation process. In that case, we can use a flow process or a bed process. It means mild condition, something between 200 to 250 Celsius degrees, from 24 bars of hydrogen in the metal and zeolite catalyst, for example. So next one. Just to show you a normal regular chromatography, you see lots of cycloalkanes production from DX. On the right part side of the slides, you can see that we also use a label 13, label carbon, and you see that carbon is also incorporating. I just put NF10 and dimethylhexane, just to let you know that the carbon from the sugar, it means the green one we marked in the slide, is observed in the final hydrocarbon. The next. Thank you. So, as it's quite important to show that the coke is present in a very, very low amount, 1.2%. Of course, because of that, we remarkable increase the conversion of carbon from the X to hydrocarbon. Next one. So, and in general, hydrocarbon are light gas that can be used as LPG, and paraffin, isoparaffin, and cycloalkanes that can be used as gasoline and jet fuel. Considering that this model compound is 65% of carbon and hydrogen, we can estimate a very high green carbon incorporation into hydrocarbon, as we see in that case, 85%. We have obtained indeed values between 80 and 90% of carbon from that's conversion from BP to hydrocarbon. Please, the next one. So just to it's a broader view, when you use model compounds of BP, when you use FCC, you do more aromatic, a little bit of cycloalkanes and olefins in the gas in the liquid fraction. When you do ADO process, we complete the class of hydrocarbons. You see, for example, cycloalkanes and paraffins and isoparaffin. The convenient use of cracking in the ADO process are able to produce all types of regular fuel. So now we move to the last paper. It was published last month in Royal Society. So it's an example of how you can use the FCC and the visual in more close to industrial condition. This is TRL5. You see that you use 535 Celsius degrees and cat feed equal to 6. We use a zeolite, that's the commercial catalyst in the fluidized reactor. You see on the right side, just in the middle, it's the picture of the units in the laboratory, and in the left side of the slide, it is real FCC units in a Brazilian refinery. So it's published. The next one. So just are the results. I just take the picture of the table of the manuscript. Next one. Next one, please. Okay. Oh, no. Okay. The first point is to see the amount of the yield of coke that's produced. Pure visual has produced around 80% of coke yield. When you put biopetroleum, it's increased, the coke increased, but not that much. Not that much. It's increased from 8 to 14, and in the middle, something between 10 and 11, 12%. Next one. So it's also important to note that the heavy fraction, it means light cycle oil and bottom that's more than an 18 carbons decrease when you use BP. Next one. Overall conversion, it means everything that's converted into useful products also increase. It's increased for 75% to 88% in the, okay, next. So it's also important to note that a huge part of oxygen from BP is released in the form of water. You see that the water is also high than the amount of CO and CO2. It's a little bit important to note that it means that you are going to lose less carbon from BP in the form of CO and CO2. Next. So the main goals of the papers is the range of BP concentration. We demonstrate a co-process from 10 to 75% of BP using typical condition of FCC units. The coke yields not increase that much and also decrease low value fractions. It means when we co-process BP, LCO and bottom decrease. Also that the oxygenation is mainly occurring in the form of water. And finally, that BP increased the overall conversion of the co-process. Next. Just let you know that what's gasoline composition, as the left side of the slide is more contain more aromatic, a little bit of more of olefins. And it's more important, when you go to the right side of the picture, you see that up to 35% of BP, we have a very limited amount of oxygenates. It means in also very low amount of phenols. So you can use you can use BP at moderated concentration. It means 35–40%, and producing drop in fraction in the gasoline. So you don't have to change or to do a post treatment if you decide to co-process BP and visual in existing refinery structure. Next. So it's the way of the gasoline in Brazil. We use aromatic in the gasoline is producing high octane number. You are able to produce drop in fraction, and also that when BP is more concentration than visual, several high value are products. You see, for example, that oxygenates are furanos and ketones, and even when you use 7% of BP, the amount of phenol is not that high. It's limited in 1.5%. Next. So we use the same, we estimate the amount of carbon that's converted into the final product as we did before. We have to create a model to explain that. Use model 1 and model 2, because we cannot convert pure but biopetrol because of the setup of our units. So there are some consideration. I'm not going to enter into detail, but you see that the carbon shows very remarkable efficiency to be converted into the final products. It's something in between 70 and 80%, 79% indeed. So very high values of obtaining from green carbon incorporation into the final products. When you see the right side of the picture, you see that BP is mainly converted. It is converted in several types of products, depending the concentration. Of course, if you can change the concentration, I'm not put here, but it's written in the manuscript, in the paper, you can change the catalyst feed ratio to produce more gasoline or more gas. It's up to, it's depending what you want. Next one. So, okay, that's it. Thank you. So this just to let you a global view. This is a diagram using O, oxygen carbon rate, and also hydrogen carbon rate. We start in the top, which means so you represent the M cellulose and also glucose, just to let you know that you are on something above 0.8 in terms of O carbon ratio, and in the middle of the picture. So on the top of the picture, we decrease the amount of oxygen in the composition. So you go a little bit down So we represent some compounds we characterize in BP, and then we demonstrate two types of process. The red one is when you do cracking, you produce aromatic and olefins and cycloalkanes. If you want to produce more isoparaffins and paraffins, you have to do ATO process. That's the blue one. And of course, the convenient use of both processes are able to produce regular fuels. Okay, so this let you a global view of the approach. Next one. Next one. Another one. Yes.
Thanks a lot, Professor, for your presentation. Any questions from the group?
Sorry, I did not finish yet. What happened?
Okay, apologies, doctor. Could you please, 1 second.
I did not finish the presentation.
Okay, apologies.
I think that I have something blocked. Okay, just to let you view, this is a global view. This is a global view of the presentation view.
Okay.
You can move to the next one. Okay, just to let you know. Okay, this is please. That's okay. So, I hope I convince you that you can convert biopetroleum using standard refinery condition in process. We saw an example of catalyst cracking and also hydrotreatment process producing regular fluid. The next one. The next one, please. This is the first part of the idea, and I'm going to present in a keynote in ECC. It's going to be in July. A full integrated and self-sustainable green refinery. It means that you can produce hydrocarbon without using regular oil. Of course, we see first using the refinery structure, then we can move to this new one. The next, please. So just to thank my group. Two of them are here, Dr. Cristiano Souza and Deborah Nobrick. Of course, all the job, all the measurements are done by the group, and thank our institution that help us and put money and then support the research. Next, please. So the main goals of the approach is the flexibility. We can use several types of biomass and ketones. We can use maturity process like FCC and also new ones, and they were able to produce a broad types of compounds that includes aromatics, paraffins, and cycloalkanes and oxygenates. The next. Just some benchmarks we have impact using this type of approach. Next. 30 seconds more. Just could you come back one slide, please? No, the next one. Okay, just to where no. We are located in the Guanabara Bay at Rio de Janeiro. This is some view of the laboratory and the place that are around the university. Next one. Okay, this is just to let you know about the structure of the laboratory. We are preparing for doing catalyst tests and catalysts and evaluates and locally and online in several types of products and reactants. Next. So just to thank you very much for your attention, and if you have some questions, please do that. I'm open to that.
Professor, have you completed your presentation?
Sorry, could you say it again, please?
Did you completed your presentation?
Did I what?
I
I finished my presentation. Yes.
Okay. Okay. So
I just open for questions. If you have some question, okay. If not, it's okay too.
Okay. So any questions from the group?
I don't know about time. I think that I had 20 minutes to present, so I don't know how much time I have consumed. I don't know.
Okay. Okay. Thanks a lot, Doctor, for your presentation. Could you please permit us whether to upload your presentation in our YouTube channel?
It means to publish my presentation.
Yes.
You ask about that?
Yes. We'll upload your presentation in our YouTube channel.
Yes, you can do that. Everything is already published in the literature.
Okay,
so don't worry.
Doctor. So, and one more thing, your conference material and your certificate and your ID card will be given to your students who are attending for the online event, for the on-site event. Okay.
Okay. Thank you very much. Yeah. Okay. Thank you very much.
Thanks a lot, Doctor, for your presentation. Okay. So let's move on to the next presentation. I would like to welcome Dr. Mohammed